Thank you, and thank you for having me. So I'm excited to be here talking to you, and I'm going to be talking about practice, like actual practice, practicing math, and good ways to structure practice in math class. So before I start rambling on, well, I already have, but I'm going to tell you a bit about myself. So I'm a mathematician. I have a PhD in math. Um, but I've also been very involved in math education and math education advocacy for about 15 years. I run an after school math program that I do as a volunteer. I co-founded it and I co-run it, and it's a nonprofit program for kids in grades 4 to 6. And I also host a podcast called Chalk and Talk, where, we talk about evidence-based practices for teaching math and education more generally. So some of you may have heard it before. If not, please check it out. So for example, I have, say, a how-to episode for how to build automaticity with math facts. Now I'd like to check that the chat's working, and I'd like to kind of know where people are from. So if you wouldn't mind, maybe you could just type in the chat your name and where you're from, and then I'll know that it's working. It's called Chalk and Talk, and you can find it on your favorite podcast app. It's also on YouTube. Okay, so everybody's from Pennsylvania, Pittsburgh, Indiana.
There was one from Quebec and another from Ontario.
Whoa, that's so exciting. Okay, excellent. Okay, so I'm just reading through here. It's going very quickly, but yeah. Okay, seventh grade and algebra, very good. Okay, fifth grade, good, 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 good. Yeah, the podcast is on Spotify, it's on Apple Podcasts, and it's on YouTube or Pocket Cast or wherever you get your podcasts. Podcast Addict is everywhere. Okay, so you could check it out if you're interested. Okay, so I'm going to tell you how I'll run the chat just because I may not notice if you're actually talking in the chat all the time because I'm going to be focusing on what I'm saying in my presentation. So feel free to write something in there, but there will be times when I sort of pause and say, can you answer this question, or could you type something in the chat? So just so you know that that's how I'll be doing that, and hopefully we can keep up. So, okay, I'm going to tell you what I'm going to talk about today. So there's someone practicing math because that practice is fun and it's important. And so these are some of the things I'm going to cover. So I'm going to talk a bit about cognitive load theory and how that can be considered when we're structuring practice. I'm going to talk about the instructional hierarchy, and I'll get into that in detail very shortly. I'm going to talk about scaffolding practice because, like I said, I'm going to talk about ways to structure practice in math class so that we can ensure that we're maximizing learning opportunities for students. I'm going to talk about something called variation theory. So we'll talk about that soon. And interleaved practice. And don't worry if you haven't heard of these things before, I'm going to explain it. Spaced practice. And then I never end a presentation without just giving some resources for math facts. I won't talk about it. If you ask me to and there's time, I will. But math facts are really important, and not enough students are fluent with math facts. So, in my opinion, and a lot of other people's opinions, so I always just like to mention that and give some places where people can go to find some resources for helping with math facts. Okay, so that's my plan for the day. Okay. Oh, and of course your questions. I'll see if we can get in some questions at the end. Okay, so let's start with this. So, and why is practice important? And why is it important to build prerequisite skills? Because as I always say, math is relentlessly hierarchical. Okay, so it's like a ladder. And so here I have this little knowledge graph, and this is just a very small piece of the knowledge graph for mathematics, which is huge. And so these are the two skills I'm talking about here at the top of this graph are long division and multi-digit multiplication. And what I'm trying to indicate is that all those things underneath, students need to be fluent in those things in order to be able to learn multi-digit multiplication and long division. So you can trace long division back, and they're even kind of interconnected, right? So you have to know your one-digit multiplication facts, for instance, and before that, you would need your one-digit addition facts. So those are kind of the foundational things that those two skills are built on. But those are just those two skills, right? That's just multi-digit multiplication and long division. But math is huge. Like there are lots of skills we need to know in math, right? And we always say, and I always think, like if you want to ensure that students have all the opportunities possible in math, you really want to prepare them for algebra. Algebra is kind of the gateway to higher level math. And so if you look at algebra, it kind of traces all the way back down and to these simple facts again. And the knowledge graph for math is absolutely huge, and it's all interconnected. And that's why I think a lot of times, and there might even be some people in the audience today that maybe you think that you're not good at math, or maybe you felt at points in your life that you're not good at math. And I think that's likely not it. I think it's more just that math is like a ladder. And if you are missing some steps on that rung of the ladder, it can be really difficult to learn those later steps. And it just starts snowballing, right? Because the more steps you're missing, the larger the gaps get, and it becomes really hard to learn those later skills. So a lot of times that's all it is. And I mean, I talk to a lot of students, right? I teach at the university level, and I hear from a lot of students who felt before that they're not good at math. But often that's not it. It's just that somewhere along the way you missed a prerequisite skill, and then everything else becomes really difficult after that, okay? So it's something that's really important to keep in mind with math. And I talk about it a lot because I know that not all people even understand that. Like it's not like, say, if you're teaching something like, I don't know, history or different things like that, you can maybe start and like do a completely different topic and it has nothing to do with the topic before that or whatever, right? Okay. So now this is a quote from the National Math Advisory Panel, and my talk today is about practice. I think everybody generally agrees that practice is important, although sometimes things that are really important like worksheets and that sort of thing can sometimes be disparaged. But I'm going to talk a lot about practice today. This is a quote from the National Math Advisory Panel. Working memory, and I'll talk about that in a second, capacity limits mathematical performance, but practice can overcome this limitation by achieving automaticity. This is from the task reports of the National Math Advisory Panel from 2008. And if you haven't heard of the National Math Advisory Panel, this group was put together to look at best practices for teaching math. So they had all sorts of people on the panel. They had teachers, they had math education people, they had mathematicians, they had cognitive psychologists, etc. And they looked at all the research, and a lot of it had to be thrown out because unfortunately sometimes the research in education isn't always generalizable. But they looked at the best, most rigorous research and gave recommendations for how to teach math, okay? So we're going to talk about these things today, about practice and getting really good at the skills you need to do well in math. So I'm going to start by talking a bit about cognitive load theory. Okay, so what's that? Well, the idea with cognitive load theory is that you want to keep human cognitive architecture in mind when you're designing instruction. So I'm going to give you just a little picture here. And so you can take a look at that for a second, okay? That's a diagram of human cognitive architecture. Okay, so cognitive load theory is kind of based on this model. All right, so it is a theory. So this is a model of human cognitive architecture. Okay. So it essentially involves three parts. Sensory memory. Okay, so you're sitting here and all this stuff is like coming at you. You know, you've got your phone dinging, you've got things outside. I can hear my colleagues, I'm in my office, I can hear them like closing their door and moving around and that sort of thing. And you've got to decide which things you're actually going to concentrate on, right? So you take those things and you move them into your working memory. And working memory can only hold so much, maybe 4 to 7 items at a time. So if I gave you a phone number right now, you'd likely forget it by the end of the presentation, unless you wrote it down or you rehearsed it, right? So you could rehearse it and then you'd remember it. But if you don't, you're likely going to forget it. And some people can remember more things. They can hold more things in their mind, in their working memory, than other people. Okay? But if we practice and we get lots of practice on, say, a math skill, we can move it into long-term memory. And long-term memory is thought to be maybe unlimited. Like, we don't know how much it can hold, but it can certainly hold a lot more than working memory. So you have a lot of things in your long-term memory, like you know how to drive a car, right? Maybe, maybe not. You know how to walk to the grocery store. If you see someone, you recognize their face, right? Like, these are things that you have in long-term memory. And when you have those things in long-term memory, you can pull them out later and you can use them again, okay? So Kirshner, Sweller, and Clark define learning as a change in long-term memory. And I think we should say a positive change, though, because we want to actually, like, we don't want the stuff we forget, right? So a positive change in long-term memory. So the idea is to move things from your working memory into long-term memory so that you can use them, right? And it's kind of like Greg Ashman says, it's like our superpower. It gives us a way to work around those limitations of working memory, okay? So the idea behind cognitive load theory is that you want to keep this cognitive architecture in mind when you're designing instruction. So you want to try really hard not to overwhelm a student's working memory, especially when they're first learning something, okay? And I think you likely have experienced this when, you know, we've all had teachers who just give us too much at once and it becomes really confusing and so you just forget everything, right? Okay, so that's the idea. So I hope that makes sense. Does that make sense? I just need a yes, just one yes. Yes, okay, I got one, I'm happy. Okay, I got a few. Okay, excellent. Okay, very good. All right, so keep that in mind. Okay. Now, I like to think of it like a bottleneck. I mean, I didn't come up with this idea. I probably saw someone else present it, but you can think of working memory and long-term memory as like this bottleneck. So working memory is like really narrow, right? And you know, not much can be held there, but if you could just like get the stuff into long-term memory, it's there, like, and it's unlimited, and you can pull that stuff out when you need it. Okay, so that's maybe an image to think of when you think of cognitive architecture and working memory versus long-term memory. So we kind of want to keep these things in mind when we're working with students, that it's best not to overwhelm their working memory, okay? And think about what's in long-term memory versus what's not. Okay, all right. And so the next thing I was going to talk about, another model that I think is really important and it's really useful for when you're learning something new. Maybe you've learned about it in some of the other sessions today. Have you? The instructional hierarchy? Have you learned about this yet today? Well, some yeses and some nos. Okay. Okay, excellent. Okay, great. So, well, that's why I'm here. I'm here to explain it. Okay. So, basically the idea with the instructional hierarchy is that when students are learning something new, they go through these 4 stages. And if you can think about what stage a student's in, then you could target your instruction appropriately. Okay, so I'm going to go through these 4 stages. All right, there it is. It's due to Herring and Eaton, 1978. Okay, and it was I probably first heard about it myself from Amanda Vanderhayden. So I don't know if she's giving a presentation today, but if she is, I would recommend going to it because she's pretty awesome. And actually, I have an episode coming out with her actually tomorrow. So you could check it out. It's actually on universal screening in math. So if you're interested in that, you could check it out. So just a plug for that. Okay, so let's talk about the instructional hierarchy. Okay, so first, when a student is first learning, they're in the acquisition stage. So they're just building the skill. They're trying to build accuracy. Okay, you're trying to get them accurate with that skill. So when a student's in this stage, they're making a lot of mistakes. I always like to give like this a skating analogy because I'm Canadian and we always talk about hockey. So you can think of learning a bike if you aren't familiar with skating. But okay, so you're teaching a kid how to skate and they just keep falling down, right? And you keep them up. Maybe you give them, like we have these little sort of carts that they can push around on when they're first learning to skate because they need that crutch, right? And you kind of eventually move them off of that to the point where they could stand up. Okay, so the acquisition stage, the student's just learning, they're going to be making a lot of mistakes. Okay, so your goal in that stage is to build accuracy. You want the student to be able to do the skill accurately. They may still be very slow, but you want to get them to the stage where they can do it accurately. Okay, and when you do that, you move to the fluency stage. Now, at the fluency stage, a student would be accurate, but they're probably slow. Okay, so if you think about back to my skating analogy, a student in the fluency stage, so they pass through acquisition, they're able to stay up on the skates, but they're really wobbly, right? So you wouldn't really want to put them in a hockey game. I mean, you could, but it wouldn't go that well for them, especially if there are other kids around that actually are pretty quick on their skates, right? So now, if it's a mathematical skill, we're talking about, you ask the student 3 times 4 and they're like skip counting by threes, right? And eventually they get to it and it's 12. So they have a way to get it, right? But they're not able to do it. It's not effortless. It's not effortless yet, right? So they're not quick at it. And you do want them to be quick at it. Like if you compare 2 students and one student is taking 5 to 6 seconds to come up with 6 times 7, and the other student can do it automatically, those 2 students are going to have very different experience when you're trying to teach them a skill that relies on multiplication facts, right? So you do want to build fluency. That's the stage at which you want them to get quicker. You want that skill to become effortless, okay? And so that's the point where you would introduce some, say multiplication fact, you would introduce time testing. Timed practice, okay? Because you do want to get them to that stage where they're able to do this effortlessly. All right? Now, let's say they can do that. Now the student is fluent with the skill. They're able to do the skill fairly effortlessly. But and there's teachers in the audience. You're probably all teachers, and I think you likely have experienced this. I experience this all the time, that I think my students can do things and I'm really impressed, and then I change something up just a little bit and then the student can't do it. Has that happened to you? I bet it happens to you all the time. So just as an example, say if you say to a student, what's 8 times 6? Student says 48. And you say, 8 times what is 48? And the student has no idea. It's like you gave them a completely different question, okay? Or, you give them a word problem that uses that skill, and the word problem is really basic, and they don't know what to do, right? Well, that's when you have to get them to the generalization stage, okay? So that's the stage at which, the student's fluent with the skill, but they're not able to use it in new situations. They switch it up and they can't use it. Well, what you have to do is you have to start giving them problems that get them using that skill in different settings, right? You still have to give them the instruction to do that. And they need to see the skill used in different settings in order to learn how to do that. So that's the generalization stage, okay? So it's sort of less, you're starting to develop flexibility, you learn how to use the skill in different situations. Now, at the very top of the hierarchy is adaptation. And that's what some people would call problem solving, innovative problem solving. So there you're giving them sort of you're sort of giving them think outside the box type problems, right? So now they've got to use that skill somehow in a very different situation, like a problem solving situation. Okay, so that's more, like if you can all of this, you can use systematic explicit instruction to do any of these stages, right? Like I've taught lots of students how to do problem solving, and the way I do it is I give them lots of examples, and then I send them off on their own. But this is the stage, that adaptation stage is the stage where if you're going to do some sort of inquiry or open-ended type stuff, that's the good spot to do it. They've got all the skills, they've got the fluency, and they're in a position to be able to use it. Okay? Does that make sense? Okay. Okay. All right. Okay. Okay, good. Okay, so you're still there. You're still there. Good, good, good. Good, good, good. I prefer in-person presentations, right? But I've taught online a lot, so I got kind of used to it during COVID. So, all right. Okay, good, good. Now, I want to just drive this point home. It's not a good idea to start at the adaptation stage. It's not a good idea to give students problems that they have not, that the skills, they haven't developed those skills to solve the problems, right? You want to get there. That's the whole point. But you want to spend a lot of time at the fluency stage, the acquisition and fluency stage, getting them really fluent with the skill. Because when they're fluent with the skill, they can use it. They can apply it in new situations. It becomes easier for them. Okay? Okay. All right. Okay. So now, I gotta keep an eye on my time here. I have this chat. All right. Now, I'm going to talk about ways to structure practice. Okay. So let's talk about it. Practice is important at all stages. That's the thing. It's really, really important to get a lot of practice. If someone asks me, what do you think, what's the most important thing? Like, what do you think is the most important thing for getting good at math? You know what I'd say? I'd say practice, 100%. And it's really the key to getting good at it. But we can be careful in the way that we structure practice. And I'm going to first talk about what I think is, I'm kind of going to go through them, maybe in the order of what I think, how I would do them. And the first one I would say is really important is scaffolding practice. And honestly, I would say throughout my career, there are times at the beginning of my career I didn't do this well enough. And you kind of look back and you think I could have really done a better job for those students. But we learn over time, and I've gotten better at it. So scaffolding practice. So let me talk about that. Scaffolding. So here's what scaffolding is. Essentially, you take a problem and you break it. Say you want students to learn a skill, and I'm going to do a few examples. You take the skill, you break it into component parts. It's very component parts, and you build them up, okay? So you gradually increase the complexity of the problem. So you start adding in new elements to the problem, and you kind of increase it. So you do this gradually. Now, let me just say, before I talk about that, let me just say, you see how this makes sense, right? When we think about things like cognitive load theory, that if we give students problems that involve too many steps, when they're first learning a skill, it's going to overload their working memory and they're going to get confused, okay? So, and then if we think about it in terms of the instructional hierarchy, you want to do the most scaffolding in that acquisition stage, okay? You want to do the most scaffolding in that acquisition stage, because that's when they're really going to need it, when they're really just starting to learn that skill, build accuracy, okay? But honestly, like if I'm teaching problem solving, I would do scaffolding. I would do it at every stage. And I have seen sometimes people will give very complex problems thinking that, well, we can kill all the birds with one stone or whatever. We can like teach all these concepts at once and like we're saving all this time. But Actually, you're not, because they're just going to get confused and you're just going to have to go back and reteach it. So you do want to really think about scaffolding, particularly when the students are first learning. Okay. So, and the other thing I should say about this is there's something that people refer to as the expertise reversal effect. And so the thing to keep in mind is when you have someone that's first learning a skill, they need a lot of scaffolding. But you want to gradually pull on, like quit scaffolding so much. Um, you want to fade, you want to fade all those scaffolding supports over time, right? Because actually it can be really frustrating. Like if you know how to do something, the scaffolding can become quite frustrating, right? So you want to do more scaffolding for novices and less for experts. Okay, so that's the idea behind it's like simple to complex sequencing. Okay, so that's scaffolding, and I will get to your questions later in the that are coming in the chat. All right, okay, so I have some examples. So I'm just curious if any of you have heard of jump math. Yes or no? Okay, okay. I mean, I wouldn't be surprised if many of you hadn't heard of it because it's a Canadian program. I mean, it is available in the US. They have a Common Core version, but it's a Canadian program and it's actually a charity. In fact, we use the tutoring version in the after school program that I run. They've also teamed up with Amanda Vanderhayden recently, by the way, to offer universal screening. So jump math is like I've never really seen a program that does scaffolding as well as jump math. I will say that. I haven't looked at every program, but I've looked, I've looked at a few, but it's really good at this. So this is an example of regrouping scaffolding in jump math. So you can see, and there would have been stuff that was done before this. I'm just showing this one particular part about regrouping. And so the skill that they're trying to teach the students is we're going to regroup. We're doing 2-digit by 2-digit, and there's a necessity to regroup, which I actually prefer to call it carrying, I will tell you, but people get so upset, so I'll just say regrouping. But I grew up with a thing called carrying. So anyway, so they're regrouping. So what they're having the students do is just the one step, right? So the student is like 5 plus 8 is 13, right? That's 1 10 and 3 ones. So your 3 goes in the ones column and your 1 carries into the tens column, okay? And don't do the next step. We're just going to do that step until the students get it. And I would say, like, if you have a student who's struggling, honestly, like you probably know this, you've probably seen it. This sort of thing works wonders. Just do a bunch of steps, like you just do it the one step, okay? And then you move on. Okay, so you can say you can see now step 2, they're going to add the numbers in the tens column. Okay, so now they're going to do a bunch with just that step. In particular, I would say long division. This is really helpful for long division, which I think some people have trouble with because there's a lot of steps involved, and so it uses a lot of working memory, right? It's that simple. Okay. Okay, so that's the first worksheet. Here's the second one. So you can see now we're going to move on to the hundreds column, right? So we're going to have to regroup our hundreds. Okay, so you can see that now we're doing the first 2 steps, and then we're going to have to do that other step. And then they're going to pull off the little box and get them to go from there. So that's an example of regrouping, okay? Or sorry, an example of scaffolding. I think is a pretty good example, okay? Okay, so I was going to see if I could ask you this question. So let's unpack a skill, and I'm gonna put an algebra problem up here, and so it's an algebra problem, but you could use any problem. It can be at any level. Any level, we need to scaffold. It doesn't matter. Here's our goal. So let's say our goal is we want our students to be able to solve linear equations. That's say part of your standards or whatever, and this is an outcome that you need for your students. You need them to be able to solve a linear equation like this. Okay, now let's unpack this. So what types of algebra problems should a student have mastered before you give this problem? So you can just type it in the chat. Yeah. Mm-hmm. Yeah, that's right. Yeah. Yes. Okay. So all these things are true. So let's say that they've already mastered the addition, subtract, like let's say they've mastered sort of the basic facts and that sort of thing, and they know how to work with integers. Let's say that's true. Okay? So just concentrating on the algebraic components. Okay. Okay. So just concentrating on the algebraic components. Yeah, they need to know all those things. Inverse operators, there's so much they need to know. But just concentrating on the algebraic components. So they would need, yeah, that's concept of equals, yeah, all that stuff. So, but on the algebraic properties, they would need to be able to solve an equation like this. Do you agree? Like that's a simpler problem than the one I have there, right? So they need to be able to solve a problem like that, okay? What else? Let's see. They're going to have to be able to do this, right? They'd have to be able to solve this problem for x, right? They'd have to be able to solve 3x equals minus 2. We're assuming they know how to work with integers and fractions, okay? All right. Now, if they need to be able to solve something like x plus 5 is 7, well, I wouldn't just do that, right? I'd need them to be able to do x minus 5 is 7, right? Okay? And I'd need them to understand that that's the same, x plus 5 is 7, like that. If I put it in a different way, like 5 plus x is 7, that they could do that too. Yeah? Okay? Okay? And they need to, not just working with negative number, like it's probably better to start with 2x equals 4, say, that, 2 divides evenly into 4. Whereas in the 3x equals minus 2, I have both a negative number, plus I end up with a fraction, right? So they need to do problems like that. And, maybe I should start with something like this too. Like if they have minus x is 2, could they solve that? Like, and what's that equivalent to, right? Okay. And then maybe minus 2x is 4. So you could kind of just go, backwards and think about these things you have to do. And you're going to want to like scaffold it in a way that you don't want to start with 3x plus 5 is 7. And I'm saying this like maybe it seems obvious, but I actually don't think it is, because I've seen it a lot that people start with the more difficult concept, the more difficult skill, without scaffolding the skills before that. And it would become so much easier if we just scaffold all the way up to that more difficult problem, okay? So I just wanted to mention that as an example, okay? All right, so, and I actually got this idea from my friend Barry Gerlich and John Mighton, who gave a presentation recently at Research Ed in Canada. And I like this animation idea, because sometimes people think like doing these very sort of scaffolded problems that it's like rote learning, or you sort of hear people disparaging it, that sort of thing. But if you think about it, it's like animation, right? Like every little tiny step leads to the big picture. It's really the big picture you want. You can see they start with the hand up there, and then like little tiny motions, and you get to the point where the hand's down there, right? So I kind of think of scaffolding like that. And you want to see the big picture. In the end, you want them to be able to solve that harder problem, but to get there, you've got to do the little tiny steps to get there. Okay? No, many books and worksheets do start in a too difficult way. That's only the beginning of the problems. But anyway, okay. All right, and then I had to put the AI generated guy there because, well, I don't know. I just felt like I had to. So, yeah. So anyway, something to keep in mind. Okay. Now, the other thing I just want to mention is I think the reason sometimes that people don't scaffold enough, I think it has to do with the curse of knowledge. So I don't know if you're familiar with this term, but it's basically when you have something in long-term memory, when you know how to do something, it can be like really, really difficult to empathize, to understand what it's like to be someone who's just learning that concept. It can be very difficult. And I know this, like I know about the curse of knowledge. I know it very well. I know it's a thing. I know it's a cognitive bias, but I still do this. And so, and as an example, it takes students a long time to get really good at a skill. So you might teach your students one day and it's like, wow, everybody's doing great. I feel so good. And like, this is wonderful. And everybody gets it. And you come the next day and it's like you never taught them that, right? But that's perfectly normal. Students, they forget stuff and you've got to keep refreshing their memory until it sticks. Okay. So I just think the curse of knowledge is something that we all really need to be aware of. Okay. Now, I was going to talk about a similar thing, and it's called variation theory. So are any of you familiar with variation theory? Kind of, yeah. Yeah, some of you, but not too many. I think it's more commonly known or used in the UK. And so I'll talk a bit about it. It's kind of similar to scaffolding. I would say it's a type of scaffolding. But the idea with variation theory is that you're teaching students a concept, and when you do your examples, you hold elements of the previous problem constant. You change one element slightly, and the idea is that students can then think about how that small change impacts the structure of that concept. Okay? So I'm going to give some examples so that you understand what I mean. So I was going to do worked examples because worked examples are good. I can say a little bit more about worked examples, but I think you probably are familiar with worked examples. So you work an example and the students do a problem similar to it. So maybe I'll say a couple things about worked examples first. So worked examples are pretty widely studied, I think. I think there's a lot of evidence that they're quite effective. And in the acquisition stage, like we talked about in the instructional hierarchy, it's particularly important that students need to study a lot of worked examples, that you need to do a lot of worked examples with students. They should be done by an expert who shows them how to do it. It's not really effective to have novice learners try to solve problems that they haven't been shown how to do. And so this is the type of thing there's lots of ways you can do them too. Like when you're first doing worked examples, you could show students how to solve a problem, and you could then put the problem up and you could be like, okay, here's your problem and show me the first step. And everybody puts the first step on their mini whiteboard, right? The other way you can do them is you can fade worked examples. So you could give like everything but the last step, and then the student does the last step. And then you give everything but the last two steps, and then the students do the last two steps. So there's lots of ways you can work them. But I'm kind of just doing the sort of general worked example here, that you work an example and then you get students to work an example. And I'm talking about variation theory. So I'd like to show you what I mean. So the first question is 3x plus 7 is 5, and you could change one element of the problem. 3x plus 7 equals 4, okay? And then the students solve that, and they have to think about what's different about that problem, if it makes any difference. Or you could do something like I said, you could switch it. That's actually the same problem, but the students don't know that, right? If they're novice learners, you switch it. That's the element of the problem that I switched was I'm trying to display the commutativity property, really, right? Okay. And then you might want to do something like that. The first one had a whole number as the constant on x, right? Or the coefficient on x. You could change it to a fraction, keep everything else constant. How does that change the problem, right? You could put a negative there. 3x minus 7 is 5. How does that change the problem? Okay. 3x plus 7 equals minus 5. This is variation theory. So it's changing one element of the problem. And I think actually I talked to Bruno Reddy about this recently. I have a podcast coming out with him in July, and he was part of the Shanghai math teachers exchange program that they did in the UK, where UK teachers went to Shanghai and Shanghai teachers came to the UK, and they shared, the Shanghai teachers shared how they teach math, because students in Shanghai do really well in math and everybody wants to know why. And one of the things he talked about was that they really lean into this variation theory. So when teachers are doing problems with the class, they use variation theory very heavily. And so that's kind of why I think that more UK teachers are using it. But I want to give you this. This is an example, and I got this from Craig Barton has a math podcast, and he has these worksheets at variationtheory.com and on all sorts of math concepts. So you could check that out. And you could grab some of those worksheets and check them out. Okay, but you can see how variation theory is incorporated here, just changing each of the problems slightly. Okay, so you could check that out after. Okay, so that's variation theory. Okay, does that make sense? You get the idea? Great, excellent. Okay, all right, very good. Okay, so next thing I was going to talk about, interleave practice. How many of you are familiar with interleaved practice? Okay, I'm going to go 50-50 from what I'm seeing. I mean, I didn't know about interleaved practice myself until a few years ago, but now I do. And I use it all the time. So interleave practice. So this is what interleave practice is. Okay, so I've got this little picture here, and this is meant to illustrate blocked practice, which isn't interleave practice. So when you're doing block practice, and I'll give an example in a minute, what you're going to do is you're going to teach a concept, and then students are going to do a whole bunch of problems like pretty close to that. Okay, then you're going to teach another one, same thing. They're going to do a whole bunch of problems pretty close to that, etc. So that's blocked practice. And you absolutely have to do blocked practice. It's otherwise you're going to create cognitive overload. So I'll talk about that in a second. Block practice is important, but I would say that we don't always do interleaved practice as well as we should. Well, it depends. Like there are some math textbooks that do it. When you do like reviews and things like that. But okay, so the idea is you want to block and then you want to interleave, and I'm going to give an example. So when you interleave, what you're going to do is, so you've taught them a topic and you're going to make sure they can do it really well. Teach them another topic, make sure they can do it really well, and then you're going to start interleaving those so that the student has to look at it and go, okay, what do I do in this one? Is it that kind of problem or is it that kind of problem, right? So here is an example. Okay, so at the top, those are blocked addition problems. And at the bottom, those are block subtraction problems. Now, I would never teach a student word problems without blocking, because I think the students would get confused if I just started putting in interleaving subtraction and addition problems, because they're not going to know what to use, right? So depending on the concept, some concepts are going to need a lot more blocking than others, particularly if it's a difficult concept. So you do want to block, right? You want to do lots of problems of a particular sort, okay? So let's say you do a bunch of blocked addition. Students get good at that. Then you do a lot of block subtraction. Students get good at that. That's great, but they can become kind of robotic, right? Because they know that they're supposed to do that problem in that way after a while, okay? So it's very important to also start doing interleaving. So after they've, pretty much mastered that concept, you would interleave. So these are interleaved addition and subtraction problems. And you see why you would want to do this because, like, okay, and again, back to the curse of knowledge. If you look at these problems and you're a novice learner, they all kind of look exactly the same, right? And how's the student going to know? Do I use addition or do I use subtraction? Well, that's why you have to start interleaving, so they have to think about it. Would I use addition in this situation or would I use subtraction in this situation? So yeah, okay, but blocking, it shouldn't be disparaged though. Blocking is important. Otherwise, how is a student going to get good at that skill, right? So they do have to do blocking and then you interleave, okay? Anyway, what was I saying? I forget. Oh, okay, right. Interleaving. So when I think of interleaving, I think of the problems being kind of similar. So they're similar enough that the student has to really think about what skill do I use? What technique do I use to solve this problem? Okay? So that's it can be anything. Someone's asking me if it should be ABC, ABC, ABC. I personally I would just start shuffling them around because they could also sort of memorize the pattern, right? So I wouldn't say it has to follow any strict pattern. I would randomize. Yeah, that would be my opinion. Okay, thank you. Okay, good, good. Okay, excellent. Okay, you get it? You get the idea? Okay, okay, excellent. But I want to say this really important thing is that because again, we don't want to confuse students. And it will be really confusing if you start interleaving before blocking. Like you need to teach them the skill first. And so do lots of blocked instruction and blocked practice and then interleave. Okay. So I would say that that's pretty important. Okay. 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 What about space practice? Have you heard of space practice? Mm. Yeah, how would you know when to go from blocked practice to interleaving? That is a really good question, and it's also a teacher judgment question. Um, but generally, I would say like if you've done quite a lot of the block practice and it looks like your students are pretty fluent with it, so I kind of consider interleaving to be a good thing to kind of put in the fluency stage the or the generalization stage. So I would say if your students are pretty fluent, you think they're pretty much mastered, I think that's a good time to introduce interleave practice. Okay? All right. Okay, so I'm going to talk a bit about spaced practice. And probably more of you have heard about that. Have you heard about the forgetting curve? What about that? Have you heard about that? Yeah. And I mean, the forgetting curve's a real thing, right? Um, so basically, the forgetting curve, you could think of it as something like this, like you could you could do a whole bunch of like cramming, right? You could do a whole bunch of cramming and you could write a test mark. Cramming actually kind of works sometimes. Believe me, I know. I have a kid in, well, I have two kids in university, but one's in the faculty of science, and in biology and chemistry they memorize a lot of stuff, and I've seen her do it. I can tell her not to, but she doesn't listen. But she will cram for her exams and she aces the exams. She's really good at it. But you might forget that later. That's the problem with cramming, right? I don't think cramming's as terrible as a lot of people may say it is, because I think you learn the information once and it's there. I think you can learn it again and it's going to be faster the next time. I think it works that way, but it's just not the ideal way to actually learn a skill, right? So you're best off if you can space out your practice over time. So I'm going to talk a bit about that. And maybe you can tell me even if you can think about some of the ways that you have incorporated spaced practice within your instruction. I would be happy to hear about it and share it. Because sometimes I actually learn a lot sometimes from the teachers I talk to. So that's helpful. Okay. So, and it's also sometimes called distributed practice, spaced or distributed practice. So you see, I've done this a few times, and I tried to use different colors in this one. And in the interleave practice one, I use similar colors because I think of when I think of interleave, they're kind of similar things. But with interleave practice, the topics tend to be a little more similar, and you're kind of going to be doing it like right after you've taught those topics. Whereas space practice, there's going to be a delay and the topics could be very different. Okay. So, yeah. So this is space practice. So again, you would do blocked practice and then you would sort of bring those different concepts in. So it could be something like you taught, I don't know, two things that are really sort of different, like graphing or okay, I'll try and keep it more basic, like area and perimeter as opposed to long division. Those are very different topics, right? But if you did long division 5 weeks ago and now you're doing area and perimeter, they probably forgot how to do long division. So you might want to bring it back, okay? All right. Okay, so that's the idea. So there's like a time delay in between your sessions. Okay. So here's an example of space practice. So your series does this, hey? That's good. So Saxon Math does this, for example. Are you familiar with Saxon Math? It does a good job of space practice. Okay, so this is space practice. So you can see it. Who knows what was being taught in that unit? It may have been the area stuff, but they're bringing back stuff from previous units that aren't related to the stuff they're doing that day, because they want to bring that back so that students they're refreshing their memory, they're more likely to remember it. A lot of people will say that, like, if you kind of forget something a little bit and then you have to practice it again, it's more likely to stick long term. Okay. So I would say generally, I actually don't think this is very common in math textbooks, to be honest. I don't know what you think. What do you think? Yeah, I think it's not common. That's like I've reviewed, I mean, I've looked at a fair number of math textbooks, but one thing I would want to caution about when you're thinking about space practice is the idea isn't, yeah, we'll hit it today and who cares? You know, if they don't get it, they don't get it because we're going to hit it in 5 weeks. That's not the idea. The idea is we're gonna learn this topic now and we're gonna do our best to get our students to master this topic. Okay? And then we're gonna bring it back again later because it's likely our students may forget it and we want them to remember it. So do you see the difference? It's not sort of like an excuse to be like, well, we're gonna see it again later, so no worries, right? You do want to make sure that we try to get them to master the concept. And then go on to your next unit, but bring it back. Okay? Yeah. Okay. I actually kind of agree with this comment. So the comment is I found the difficulty with Saxon was that if they didn't already learn, there were so many topics that the student didn't know how to do, and I was having to teach 3 different topics. See, that's what I'm talking about. So that's where you could run into trouble. If the students didn't master the concept the first time and we're doing space practice and we have a lot of stuff going on, it could actually be quite difficult. You probably want to keep it simple, like not put in too many. Okay, good. Yeah, no, these are some good comments. All right. Okay, so that's the idea between about space practice. Okay, and I lost my main chat. There it is. All right. Okay. Now, I wanted to ask you about some spaced practice techniques, and maybe you can put some notes in the chat and I'll be happy to share them. So I was going to mention a couple. One is daily reviews. So coming in and, okay, we're going to review. We did this one topic a few weeks ago. Here's a problem. Do you remember how to do it? Right? And then you'd have to build that time in. Like you're going to have to show them if they don't know how. Cumulative quizzes are good. Last lesson, last week, last month, I got that idea from someone. Oh my goodness, Blake Harvard. So he does that. So he'll do this maybe every Friday. Let's do something from last lesson. Let's do something from last week. And let's do something from last month. Okay? So do you have any ideas to share? Main chat. Nothing to share. Throwback Thursday. Yeah, that's what I'm talking about. Exactly. Throwback Thursday. Exit ticket. Tic-tac-toe. Bell ringers. Remind me what bell ringers are? And math mysteries. I don't know what that is either. Yeah, review. Yeah. Problem of the day. Yep. As long as problem of the day are problems they know how to solve. Okay. Okay. So I'm getting some good stuff in the chat, and some of it, there's some acronyms here, and I don't know what they mean. Okay, there we go. I do math mysteries. They are 5 clues of 5 previously learned skills. Okay. Okay. No, these are great. So, and if there's anything else, yeah, throw it into the chat. Space learning over time. Yeah, you can do mini whiteboards for your things. You can also do like well, if they have mini whiteboards or cue cards or something like that, and you have the cue cards and you put up, you can do multiple choice, like to review, and everybody hold up the answer, and they have A, B, C, or D, and they hold up the right cue card. A lot of core programs add these in with a daily warm-up that is previously learned skill review quickly at the beginning of the lesson. Yeah, no, that's excellent. Those are really excellent tips. Okay. Okay, that's great. All right. Okay. So, yeah, so thank you for sharing that. All right, the idea is just to kind of try to keep bringing stuff back. So interleave practice, you're kind of doing that within your lessons, and you're taking skills that are kind of similar, and then the students have to differentiate the skill. Space practice, you're bringing back concepts over time, right? Okay, so I hope that makes sense. Okay, thank you for explaining your acronyms. Okay, excellent. I wanted to give you some resources for learning math facts. Math facts are really important. And, you know, if I had to say, how many of you are elementary school teachers in this session? I'm just curious. Lots, right? Okay. So good. So important. So important. Elementary school. It's like, it's honestly like it's the foundation for everything, right? So, and I always say math facts are a gift. They're like one of the greatest gifts you can give your students. You can make sure students actually gain automaticity with math facts fairly quickly with effective methods. So I have a whole practical guide on automaticity with math facts. So the 4 things we talk about, and it's based on Brian Ponce's mind program, Facts on Fire. and I think he's giving a talk at this conference, and I would highly recommend going to see him. He's got this free program and it's really great. So, and I did a little practical guide. He helped me with it. So it's only about, I don't know, 35 minutes. And I kind of go through 4 techniques for math facts. The first one is cover, copy, compare. Or actually the first one's probably flashcards. Flashcards. So you want to do your flashcards in small set sizes. You figure out what are the facts that the students know versus what are the facts that they don't know. You take a small number of the ones that they don't know, and you go through those for like 3 days, right? And then you replace them with new facts. So that's kind of, I talk about that. I talk about cover, copy, compare. I don't know if you're familiar with that, but I explain that in detail. So that one, it's like you see the math fact, you read it to yourself or you read it out loud, and then you cover it up and you try to remember it. Okay, so that one's good. And then taped practice. So he has these little tapes where the person reads out the math fact and then you try to beat the computer. So you say them, you write down or you say the math fact before the computer, and it's kind of like a fun game. So he has a whole bunch of those. And then the last one's time practice. And do you know when to do time practice? Do you know what stage you do timed practice? I'm just out of curiosity. Yeah, you want to do it at the fluency stage. So I think there's a lot of dialogue about time practice, and that people are worried about timed practice. They're worried about it causing anxiety and things like that. But the key really is to make sure you're doing it at the right stage. So you want to do it at the point where the students are pretty accurate. Like Robin Cotting told me, about 90% accurate, and then you're ready to build up that speed. So that would be a good time to introduce the timed practice piece. Okay, so it comes in at the fluency stage. So I talked in quite a bit of detail about those things in that practical guide. So check it out. And if you like it, share it with everyone, because I'm on a mission to make sure that all kids know their math facts. Okay, so I would appreciate it if you shared it. Okay, so yeah, I have 2 episodes with Brian Ponce actually. So he's really great. Okay, and then the last thing I wanted to tell you about, do you know about this guide, the IES practice guide for assisting students struggling with math? Some of you do and some of you don't. I mean, I didn't know about it. Again, probably first introduced to me by Amanda Vanderhayden, who I think very highly of. And so yeah, you could check out this practice guide. It's the IES practice guide. And basically these have been well researched. They get a working group together to look at best math practices for teaching math. And you can see these 6 things are on the list. So systematic instruction, provide systematic explicit instruction that's got strong evidence. Mathematical language, I didn't talk about any of these things today, and representations, and number lines, word problems, and timed activities is on the list, because it's, we do have to make sure students are fluent, otherwise they can kind of fall off the math track, right? If those skills are not mastered. So I wanted to mention some of those things. So yeah. Okay, so I have like 10 minutes left. So can you go ahead and ask some questions? So please, if you'd like, ask some questions in the chat, and if I can answer them, I will.